Hi, welcome to Market Board Videos. Today's video is about the law of conservation of energy. And we talked about laws of conservation before. This is another law of conservation. And when you say law of conservation, all we're talking about is it has to, some quantity, some characteristic has to remain the same. So in this case, we're talking about energy. And basically it says energy cannot be created nor destroyed. It can be transformed from one form to another, but the total amount has to be the same. So it can change, like if you've ever seen in Star Trek that shapeshifter guy, that's the same guy, same stuff, but he changes from one thing to another. Well, that's what we're talking about. It can change forms, but you're never going to have more of it, you're never going to have less of it, you're always going to have the same amount. So let's do a couple of examples. So this is my little wind-up. I know it doesn't look like it, but it's my little wind-up car, and we wind it up and we put some energy into the spring. In fact, we're going to give it a potential energy of 10 joules. So since it starts out with 10 joules, it has to end with 10 joules. If we let it go, it moves in that direction, and we find that it uses 8 joules or it has 8 joules of kinetic energy based on its velocity when it reaches this point. So where did the other 2 go? Well, the other 2 joules probably went into heat or sound. 8 and 2 equals 10. So what we have, what we started out with, that's what we have, what we end up with. Here's another example. You have a pendulum that's swinging back and forth, a bob on the bottom of a pendulum. So it starts out with a certain amount of potential energy, and as it starts to swing, when it's partially, not quite down exactly straight, but straighter than it was, it's moving. It has a combination of potential and kinetic. When it's down at the very bottom, so it can't go any lower, it's all kinetic, no potential. And then it swings back to this side, and it's potential and no kinetic. So it can go back and forth. It doesn't have to stay in one type of energy. In fact, it does go back and forth. The total amount of energy is conserved. So if we had 10 joules here, this might be 8 kinetic and 8 potential and 2 kinetic. This would have to be all 10 kinetic, and this would have to be all 10 potential. So your sum, the total, has to stay exactly the same. Let's do one more example. You have somebody standing on the edge of a building or the edge of a cliff or whatever. There's a skydiver. Down here you have the little safety net, you know, that the guys stand and hold that you can fall into, kind of like a big old airbag. Up here the potential energy is 10,000 joules, no kinetic energy because there's no motion. As the person starts to fall, their speed picks up, they get closer to the ground. Because they're closer to the ground, their potential energy decreases. Because their speed increases, their kinetic energy increases. 7,500 and 2,500, if you add those together, you get your 10,000 again. Exactly halfway down, they still have half the distance to fall, so they still have a potential energy, only now it's 5,000 joules. But now they're traveling a little faster, so their kinetic energy is also 5,000 joules. 5,000 and 5,000 makes 10,000 joules. Your sum is still the same. 3/4 of the way to the ground, they don't have very much further to go. The potential energy is down to 2,500 joules. The kinetic energy, now they're really moving, is 7,500 joules. And finally, right before they hit the bottom, right before they hit that big old airbag that they're going to land in, the potential energy is 0, and the kinetic energy is 10,000. The sum of those equals 10,000. If you add these up all the way across, you'll see that each one equals 10,000 joules. And that's what we mean by conservation of energy. Let's do a couple of energy problems in work and force problems. So, how much work is required to increase the kinetic energy of a car by 500 joules? Well, we know that work is equal to change of kinetic energy, and I told you kinetic energy was going to change by 500 joules, so that's how much work you must need, exactly 500 joules. One more problem. What change in kinetic energy does an airplane experience if it is moved a distance of 500 meters by a sustained net force of 5,000 newtons? So we have our no-Watton formula grid. We know that it's 500 meters. We know the force is 5,000 newtons. We want our change in kinetic energy. Work is equal to change in kinetic energy. Work is also equal to force times distance. So our change in kinetic energy equals our force times our distance. It's 5,000 newtons times 500 meters, which gives me 2,500,000 joules, or 2.5